For quite a while, people have envisioned what life might be like in other universes. On account of the James Webb Space Telescope, the most remarkable telescope in existence, that question can at long last be answered. While observing the nearest star system to us, Proxima Centauri, which is just 4 light-years away, researchers have seen a few unexpected inconsistencies from one of the planets in the system, Proxima B. These abnormalities, called fake lights, have confused the best minds in mainstream research. But what are they? Do these lights suggest the presence of intelligent life on the planet? Join us as we explore James Webb's alarming discovery of city lights that change everything. The only life that we are currently aware of is on Earth. Since the beginning of human civilization, people have questioned whether there is life elsewhere in the universe. To conduct such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The task's goal is to gather spaceborne radio transmissions. Radio waves can travel farther and are thus more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains, because they are less scattered or absorbed than other types of radiation. Yet, for 30 years, no obvious extraterrestrial signal has been found. After that, the James Webb Space Telescope's successful launch helped with the quest to examine a range of distant, unseen planets circling faraway stars. The largest telescope on the planet, which is drifting around 1 million miles from Earth and equipped with incredibly sensitive detectors, will be utilized. A long time ago, there were no known planets outside those in our solar system. However, since then, more than 4,000 planets, also referred to as exoplanets, have been found circling different stars. According to NASA, the universe may contain trillions of exoplanets. The earliest indications of life beyond our solar system might be found in extraterrestrial vegetation. The Galileo spacecraft turned its instruments back toward Earth when it was on its way to Jupiter and found a definitive sign of the presence of plants. The instrument detected the vegetation red edge, VRE, biosignature, a combination of red and infrared light reflected by plants. For example, a planet like Earth that is covered in a jungle should have a strong and easy-to-detect VRE signal. EJWST will measure the VRE of faraway Earth-like planets in the habitable zone around stars. They could be significant indicators of life in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST might be able to detect it as it enters its atmosphere. The light's missing frequencies would then be found through spectroscopy. Atoms and molecules in the atmosphere absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This technique might be used to determine the composition of the air and whether life is possible. It is probable that life could exist on Earth-sized planets with atmospheres like our own, with a combination of oxygen, nitrogen, and carbon dioxide. By looking for components that aren't naturally present, one might be able to detect mechanical life. Chlorofluorocarbons, CFCs, produced for use in refrigeration and cleaning products would most likely be observable to extraterrestrials observing Earth's atmosphere from a distance. If the JWST detected CFCs in planetary atmospheres, that would be an obvious sign of civilization. Life on exoplanets could look completely different from life on Earth. Sometimes, even naturally similar extremophile species can seem alien. Extremophiles are a group of organisms, primarily microorganisms, that can endure conditions where other living things would die. Some can survive heat up to 250 degrees Fahrenheit. Others can endure cold as low as -4 degrees Fahrenheit. Some can survive in strong acids with pH levels under 3, while others can be found on Earth in places where we wouldn't expect to find any life at all. Yet, since planets like Earth are more likely to support life than planets with extreme temperatures or acidic conditions, it might be a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces or orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are rarer and typically have shorter lifespans in our universe. The likelihood of considering planets orbiting around red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. There is more opportunity for the development of life and evolution to produce complex life forms because these stars have significantly longer lifespans. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone could have liquid water on their surfaces. Despite having a much smaller and colder mass than our Sun, the TRAPPIST-1 star emits light that is similar to that of Earth. The best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our closest star. Proxima is around 600 times fainter than the Sun, so a planet must be much closer to it than Earth is to the Sun for it to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable region, in a Goldilocks-like zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri. It's possible that Proxima B is an airless, dormant planet, given that it orbits its red dwarf star at a distance of just 4.6 million miles. The distance between the Sun and Earth is 93 million miles. The planet Proxima B is in a close orbit that exposes it to strong solar winds that can completely destroy its atmosphere. It also provides enough sunlight for temperatures and liquid water similar to those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, continuously showing the same side to the star as the Moon does to Earth. Proxima Centauri is around 1/8 the mass of the Sun and consumes significantly less brightly than one might expect. For a planet so close to its star, only 5% of the Earth-Sun distance might be expected to be an intensely hot ash. Liquid water could easily exist on Proxima B as long as the planet has an atmosphere to retain heat. Since the total energy reaching it from the Sun is only 65% of what Earth receives, however, the planet is not particularly hospitable to life. It is probably tidally locked, which means that it always faces the same direction toward the star, creating permanent day and night sides with extreme temperature changes. The planet also receives 100 times more high-energy radiation than Earth does because of its proximity to Proxima Centauri, including X-ray and ultraviolet light. Proxima B is also bombarded with high-energy particles during stellar flares. Unless it has a shielding magnetic field like Earth's, the planet's environment is less likely to escape. However, there are certain conditions that could make it a pleasant world. Unfortunately, models suggest that the atmosphere of tidally locked planets may be vulnerable to a rapid breakdown due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we couldn't guess whether the planet has an atmosphere. But since an atmosphere implies the presence of oceans, and the two taken together imply the presence of life, we are desperate to know if Proxima B has a sophisticated civilization. It could have solar panels covering the day side to generate power to light and heat the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered a race to determine whether it transits its star's face as seen from Earth. These transits would allow researchers to determine the planet's size and mass, which would then enable them to determine its density. Knowing that would confirm the planet's rocky composition and provide information on the materials used to make those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere. However, the likelihood that the orbit will be in the right alignment for researchers to see a transit is only 1 in 12%. The star's tendency to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is interesting as its heat makes a rocky planet absorb sunlight and emit it as infrared light. However, rocky planets produce a distinctive kind of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was made specifically to study infrared light. Proxima B's infrared heat signature is the key to identifying the planet's atmosphere. The infrared part of the spectrum has a strong affinity for Hubble's successor. For the first time, scientists will be able to measure how much water vapor is in the atmosphere, determine the abundance of different elements like carbon and oxygen, and estimate the temperature of the atmosphere in depth. Using the spectrum that Webb is planning to observe, they can use the data to draw conclusions about the planet's overall composition, as well as how, when, and where it formed. The best fit model, represented by the blue line on the chart, accounts for the data, the known characteristics of WASP-96b and its star, as well as the attributed properties of the atmosphere. Modern web architecture has made it possible for these measurements to have such outstanding clarity and detail. The 270-ton gold-plated mirror effectively captures infrared. Astronomer David Kipping of Columbia University says the star is interesting as its heat makes a rocky planet absorb sunlight and emit it as infrared light. However, rocky planets produce a distinctive kind of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was made specifically to study infrared light. Proxima B's infrared heat signature is the key to identifying the planet's atmosphere. The infrared part of the spectrum has a strong affinity for Hubble's successor. For the first time, scientists will be able to measure how much water vapor is in the atmosphere, determine the abundance of different elements like carbon and oxygen, and estimate the temperature of the atmosphere in depth. Using the spectrum that Webb is planning to observe, they can use the data to draw conclusions about the planet's overall composition, as well as how, when, and where it formed. The best fit model, represented by the blue line on the chart, accounts for the data, the known characteristics of WASP-96b and its star, as well as the attributed properties of the atmosphere. Modern web architecture has made it possible for these measurements to have such outstanding clarity and detail. The 270-ton gold-plated mirror effectively captures infrared light with its size and accuracy, with little to no obstruction from other objects in space. A machine that can measure the spectra and find the essential gases, water, and methane, using the information from this instrument, gives the Webb telescope the ability to identify the target's atmosphere, gases, and other elements in the air.